Alright, this is going to be the last substitution we look at in forms of substitution. And what we're going to look at is things that have coefficients in front of the variables and a constant term. And so we basically have two different linear systems. Around the differentials, where A1, A2, B1, B2, C1, C2 are constants. So we have constant coefficients, linear coefficients. This is a linear system, and we can arrange this so that dy dx, there's some negative sign out front, is A1x plus B1y over A1x plus B2y, right? And we'll deal with the constants as we progress, and you'll see it'll come. This is the general form. Well, this is homogeneous, but what we're going to do here is we're going to change the axes, and this change of axes is, if you can think about it, there's x, or there's y, there's x, and we're going to do some change where we're going to do x is some u plus h, so u plus h, so if I come back here, there's u, and y is some v plus k, so there's k. And so I do this shift of axes. I shift my origin down to this new place, and I do that by just defining x equals u plus h and y equals v plus k. And what happens is, if we put this in through here, we get a system of equations where y h plus b1 k plus c1 equals 0. And A2H plus B2K plus C2 equals 0. And we get this new linear system, which redefines this as y plus B1 V over U, because it's homogeneous, A2 plus B2 V over U. And we've pooled all of the variables, instead of being two separate terms, into one term, one homogeneous term. And we solve this system to find h and k. So let's look at one here. We're using the linearity of these systems to convert it into a form where it's purely homogeneous. All right, let's do one. And I think you'll see how this goes. So negative 3x plus y minus 1 dx plus x plus y plus 3 dy equals 0. And so we're going to turn this into a linear system. We're going to take the coefficients, the constants, and we're going to say negative 3, 1, and negative 1. Okay, so I'll take this line here and I'll write this out. Negative 3x plus y minus 1 equals 0. X plus y plus 3 equals 0. I want to turn this into a linear system. So this becomes negative 3x plus y equals 1. X plus y equals negative 3. And I'm going to turn this into a matrix form. So negative 3, 1, 1, and 1, 1, negative 3. It's my row echelon form of these coefficients. And I'm going to solve this system because this column represents my h values and this column represents my k values. And so H and K come through the linear system. Now I could solve this linear system through elimination or other means, but I think, linear algebra, right? It's taught in college algebra and high school algebra for a reason, and that reason is it gets us through these systems rather quickly. So I'm going to swap my rows. I'm going to put this row up top since I'm free to do a row swap. And then I'm going to take 3 times the first row, 3R1, and I'm going to add it to R2 and put that into R2. So 3 times this plus this is 0. I'm not changing my first row. 3 times this plus this is 4. 3 times this is -9 plus 1 is -8. That's my new. And now I'm going to take row 2 and I'm going to divide it by 4 and put it back into row 2. So 1, 1, -3 gives me 0, 1, -2. Well, at least I know my K value is -2 because this is coming through. And now what I'm going to do is I'm going to take R1 and I'm going to subtract R2 from it and put that back into R1. So 1 minus 0 is 1, 1 minus 1 is 0, -3 minus -2 is -1. And my final matrix is diagonalized, and so H is equal to -1 and K is equal to -2. And so I was able to use the system. So I used my linear system and I solved them, and when I solve them, this becomes the H and K values. What I get for here will determine my H and K coefficients. Well, now that I have H and K, I can begin my substitution. And so I said X was equal to U plus H, so X is equal to U minus 1, and I said Y is equal to V plus K, so Y is equal to V minus 2. And if I do a little switching, U is equal to X plus 1, and V is equal to Y plus 2, if we want to keep track of those. And so now I can come back in and I can substitute into the form where I had A1 plus B2 V over U over A2 plus B2 V over U. And in solving this, right, I have dV du is equal to 3 minus V over U and 1 plus V over U. Alright. Let's look at this in a second, where this pulls from. So if I do my substitution, so if I do my -3x plus y minus 1 dx, and I substitute, and so this becomes -3u plus 3, because I'm substituting this in for x, plus v minus 2 minus 1 dx. That's my dx term. And so collecting terms together, I get minus 3u plus v minus 3 positive 3. See how they went away and I'm left with just two variables. My constants dropped out. And then let's look at my other term. Come back up here. I want to substitute in, where did it go? Just had that visually. Oh, I wrote it down there. X plus y plus 3. So, x plus y plus 3 dy equals 0. And so I'll come in here. X is u minus 1. Y is v minus 2 plus 3 dy. And this now becomes, oh, and I'm sorry, these becomes du and dv because I've done my substitutions. Du. And so minus 1 minus 2 is 3. And I get u plus v dv. And so when we solve that linear system, we solve it in a way that the constant terms go away. And so this linear solution to the system of these two equations, which was what was the dx time and the du, when we solve this and we get the h and k, we've eliminated the c constants. And that's what we get here, negative 3u plus v du. And when I swap it back in, I've got that. Well, this is homogeneous, and this we can solve with homogeneous terms. And so what we've done is we've taken a fairly complicated problem and through a nice linearization have gotten it into a fairly less complicated problem. Not easier. Well, easier, less complicated, but still complicated. All right, so we need to then think in homogeneous terms, and we're going to say, hey, z is equal to v over u. So let's see, dv du is equal to z plus u dv du, right? If I multiply this over here and take a derivative within u, I get z plus u dz du. And now I can do my substitutions. So dv du is equal to z plus u dz du. So z plus u dz du is equal to 3 minus z, 1 plus z. Now I can solve u dz du is equal to 3 minus z, 1 plus z minus z. Alright, here's where the nasty comes. Get a common denominator. I'm going to keep my equal sign here. So u dz du is equal to 3 minus z, 1 plus z. Well, now I'm going to 1 plus z times this, so that's z plus z squared over 1 plus z. Putting these all together, I get 3 minus 2z minus z squared over z plus 1. Whew. Alright, well that's not too bad. I'm out of space, so let me zip over here. Yeah, I'll zip over here. And so I'm going to, we'll just remember to scroll right. And so dz, let's cross multiply, so this is my term over here, so I get z plus 1 over z squared plus 2z minus 3 dz. And notice I told the negative sign, I'll leave that over here, negative u, or whoops, negative du over u. Alright. That's, well, we've seen this guy before, unfortunately. So we're going to integrate both sides. So the integral of z plus 1 over z squared plus 2z minus 3 dz is the integral of negative du over u. Here, we keep going this way. Yeah, good. Alright. Well, to get this first integral, I'm going to have to do z over z squared plus 2z minus 3 plus 1, oops, the integral of 1 over z squared plus 2z minus 3. Alright, I'm breaking apart the numerator because we can do that. They have common denominators, they go backwards and forwards. Keep my dz's here. And that's equal to the negative du over u, who's just hanging out there in the end going, which is about how I feel. Well, this one is nasty. But if we take our trusty Chalmers, recognize the form, plop down into my tables of integrals, and recognize that I have seen this one over and over again, and we want things that involve quadratics, and this was the nasty integral. And so integrals involving ax squared plus bx plus c, 17.2, 17.12.2. And so that says that I want to take 1/2 of ln of z squared plus 2z minus 3 minus the integral of b over a, but b is 2, and so I get the integral of 1 over z squared plus 2z minus 3. Sorry, z squared. But hey, I've got one of these positive here too, so they're going to cancel out. So I don't even bother why I'm writing it. I know it's going to cancel. Equals the negative du over u. This form, I don't know why. I've been tutoring and teaching Calc Diff EQ. This particular form pops up a lot. And this separating the top out, sometimes it's in a way where you have to force the separation up top. And then this first part, partial fractions, will get you this form out of it. But in general, it's a nice integral to find. But recognizing that we have to separate this is part of the form that we look for. All right, so I've separated that back out. I know these two cancel. Yay. And so, and this thing here is ln of u, right? And so I get 1/2 ln z squared plus 2z minus 3 is equal to ln of u plus c. Okay, I'm going to multiply by 2, which is going to give me, I'm going to multiply by 2, so I get 2 ln u plus c, because 2 times c is still c. And I forgot my negative sign hanging out there. I'll keep my negative sign back. That's good. And this is ln z squared plus 2z minus 3. So I'll take e to this side and e to this side. And I have to multiply that in through there. And so I get z squared plus 2z minus 3. Because I took e to this and it canceled. Well, if I bring the negative 2 into there, I get 1 over u squared. So I get 1 over u squared. So I'll make, and e to that brings the c out front to u to the negative 2. Ah, but wait a minute, this was z. Oh no. Oh no. It was z, but I didn't start in z. I need more space. How do I get more space? Oh, let's add more space down. Let's see if I can add more space down to the bottom of the image. So, resize, canvas. I want to anchor on the top, and I want to add 600 pixels down below, 1200 pixels down below. Let's see if that's going to be good enough. Yeah, there we go. That's the 1200 pixels for you. Well, z was v over u. So this gives me v over u squared plus 2v over u minus 3 equals cu to the negative 2. Well, I can multiply everything by u squared. And so I'm going to get a u squared over u squared. I'm going to get v squared plus 2vu minus 3u squared equals c. Cool. Well, that's better. But wait a minute. We started this whole thing out way, way, way up here. With these translations. Right? And so we say y is v minus 2 and x is u minus 1, or v is y plus 2 and u is x plus 1. So So I'll get back down over here. So if v is y plus 2, I get y plus 2 squared plus 2 times y plus 2 times x plus 1 minus 3 x plus 1 squared equals c. And there's the solution to our differential equation. Yay! We did it. This type of linear substitution takes some getting used to. The form doesn't pop up that often, but when it does, this is really, it's your only way out of the nonlinear mess. And so what you want to do is, if you see that you can get, going back to where our example started from, linear coefficients in front of dx and linear coefficients in front of dy, you can solve to get your hk, and this substitution of hk, this transformation to u and v, will get you a homogeneous equation, and you can solve. If you don't do it this way, it's really hard to find the homogeneous solution in the other form. And so this double substitution is a way out of a hole. And like I said, nonlinear things, we're not going to have many ways of solving, and so this way of forcing linearity on this is helpful.